to thank everyone here today for joining us. We have today with us Jose from Fuji Electric, and also Matt Angel and myself are going to present briefly through today some of the concepts that we're utilizing for VFD technology. So I'm going to go ahead and start with this short video here. I'm not sure if a lot of people have seen this yet or not, but this is what we're going to talk about. Perfect. Now we're set.
Yes. Okay, perfect. So thank you, everybody. Thank you for joining. I would like to explain a bit, talk about the pumping irrigation, the solar pumping in irrigation. So the topics will be what's solar pumping, why solar pumping, typical solar pumping applications, electrical topologies that we can meet with our drive, basic control signals and wiring to have an idea, and then solar panels and PV systems, some ideas about how to size. We are not experts on that, but we give some ideas. Desired features of solar pumping inverter, and then some topics as a conclusion. Basically, with solar pumping, we have a PV solar system feeding an inverter, and this inverter is supplying energy, supplying current to a pump, and then we are pumping using this pump for pumping water. So why solar pumping? One of the reasons, in some areas it's difficult, or they don't have access to the grid, or as well may imply high cost. So solar could be an alternative. The cost of the electric power will continue getting higher and higher. Solar, we know how much it's costing us. Generators located in remote areas with increasing costs as well is another of the reasons that may make solar pumping interesting. In some countries, especially in development, for example, this happens in India, the demand of the electric power is higher than the production, and this creates a serious quality problems in the power grid. Solar could be one solution in these countries. And I think very important, sometimes the farmer has already the PV field in place, and then that's the largest cost of a pumping system. So to continue applying a solar inverter and a pumping system based on solar inverter could be much less costly. Or, of course, just willing to go green. Why not? Is exactly the season with the higher solar irrigation matches with the season of the higher water demand. So that's an advantage for solar systems. Typical applications, we may have a solar system supplied by panels and as well by generator or the grid, and then pump into a tank, storage, or on the right side, we can see the system is directly pumping to drippers or sprinklers. Topologies. There are three main topologies, and I think that's a bit the topic of today. The drive allows us to have three different topologies with the solar as a main supply of energy. The first one is off-grid. Off-grid, as the name says, we have a solar system feeding the drive, and this drive is feeding the pump. And the point is, since we are feeding the system and the only energy coming to the drive is through the PV panels, the PV system, so we can pump only when there is energy, only when there is enough sun, enough radiation. The second system is a selectable power supply. Selectable means we can take the energy coming from the PV panels, or we can switch and take the energy, the power from a generator or from the grid. So as the name says, selectable means we take it from the panels or from the generator or grid. So we need an external system to switch, an automatism to switch between these two energy supplies. And the third one, I believe this could be very interesting, is the simultaneous power supply. Simultaneous means we have energy coming from PV panels, and at the same time, we have the inverter, the system, watching the energy from the panels, and if needed, if we don't have enough energy coming from the panels, there is not enough irradiation, then we take the energy from the grid, or we take the energy from a generator. So in this case, the system can be done, the drive can automatically take the energy from where he believes is the most efficient system. If we have enough, we take from the panels, if not from the grid or generator. Main advantage, of course, is a cost. Here we are saving the cost. We are not taking the energy from the generator or from the grid. This slide is showing a control signal, very basic. This is an example of off-grid. So we can have just one signal, one command, which is run forward reverse in case of drives, in order to operate the system. That's all. There are functions. There is a digital input that is forward reverse run command. This means run permission when it's on. A digital input, tank level, high level. Tank is at the maximum level. So when it's on, this input means run is not allowed. There is a digital output, low power indication. When this signal is on, means the power is lower than the expected value. This means the power coming from the solar panels, it's not enough to run the pump. Another digital output is tank full. In this case, is an indication on off of the tank maximum level, storage at the maximum level. So if it's on, means the tank is at or above the maximum level. There is another alternative, and it's an analog input giving us a sensor, giving us a tank level signal. We may want to stop the tank not at 100%, maybe at 60% or 80%. Maybe the season does not require that we have the tank full, and then we can put the tank or stop the tank at 60 or 80%. In this case, this analog input is showing the tank level signal and the analog signal to indicate the tank level. And then we can program at which level we want to stop the system. Wiring. This is the wiring for off-grid when we just have solar panels supplying the system. In this case, the positive, first, the panel should be isolated, poles isolated. The positive should go to the entrance of the drive, 3 lines, L1, L2, L3, and the reason is to split the current among the diodes. So not one diode is taking all the current from the panel. So we are using the diodes at the entrance, and the negative goes to the negative of the DC bus. Advantages of the system is a very simple system. As I have explained before, just one signal can have the system running. Uses the charging circuit of the inverter to protect the capacitors of the inverter. That's the main reason to take the entrance of the inverter. Using the diode bridges offers an extra protection, but has as well some disadvantages. The maximum number of power-up sequence means an inverter cannot stop many times, has a limited times per hour, because there is a charging circuit and there are some limitations. So that's one of the limitations of having this off-grid system. And of course, is fully dependent on the PV power, on the radiation. If we don't have enough, we cannot pump, and then there is nothing to do. Second system, selectable power supply, wiring, same. We have the entrance, the positive at the entrance of the inverter, and we have the negative in the DC bus. Here we have a switch in order to select if we want DC coming from the panels or if we want AC coming from a generator or from the grid. Here we have the entrance when it's coming from the generator or from the grid and AC power, one or the other. Advantages of the system: AC supply when there is not enough photovoltaic power, so we can always switch if there is not enough power. Using the charging circuit of the inverter as well as a protection. Has some disadvantages. We cannot have with this system DC and AC at the same time. We select photovoltaic or AC power. External sequence is needed, so we need an automatism that makes the switch. And the last is simultaneous power supply. Here we have both connected at the same time. In case of DC, we have the connection through the DC bus of the drive. So before was at the entrance, the positive, now is a DC bus directly. And we need diodes, protection diodes here at between the panel and between the drive. And of course, AC, we have the AC at the AC of the drive. But in this case, both are connected at the same time, and it's the drive who selects where to pull the energy from. Advantages: sharing the load between the panels and the AC supply. It's possible to operate when there is no solar power available, but has as well some disadvantages. It's difficult connection and the control of the power is a bit more complicated. A careful panel voltage selection is needed. So here, since we have both the panel and the AC at the same time, we need to carefully select the voltage of the panels. So we need some engineering support here. And external diodes, in this case, are mandatory. This is an example of simultaneous supply where it's connected. We have a drive. It's a 1.2 kilowatt pump, so 1.5 kilowatt drive. It's a cloudy day. Later we will see a bit. And this graph shows 7 a.m. to 12 p.m. So the drive is continuously checking if there is enough power coming from the PV panel. There is not enough. And we see around 8:38, 8:45 starts taking power energy from the panels and goes up to basically 100% around 12. Later goes down, and this goes down is exactly because it's a cloudy day. Otherwise, would continue taking the power from the PV panel. Second slide is the same system, now from 12 to 6 p.m. And here we can see that sometimes takes the power from the PV, but there are some clouds, and then we need as well additional power coming from the grid. So the drive is taking the power and is keeping basically a continuous power to the pump. We have, of course, solar panels, and as we know, we need to optimize the power that we take from the solar panel. So under the solar irrigation, the solar power supply electrical energy. And this is very much dependent on the irradiance level and the temperature. And depending on these conditions, the drive is searching always the maximum power point tracking. Okay, that's what the drive, one of the functions that the drive is doing. And as I said, depending on the temperature, depending on the irrigation, we need to select the proper panels. Typical installation has between 1.4, 1.8 times. Now I am talking about the panels. How many panels do we have to connect to the system? So our experience says between 1.4, 1.8 times the capacity of the pump. So if we have 11 horsepower or 10, let's make it easy, we can put 14 to 18 horsepower as a panel. The number of panels connected in series shall not exceed the maximum input voltage in open circuit, because there is a limitation with the capacitors of the inverter. Otherwise, we could damage. Here we can see, depending if it's 230 or 460, the minimum and the maximum voltage that we can fit and some recommended voltage. But again, this is necessary to consider at the minimum ambient temperature, because the lower the temperature, the higher the panel output voltage is. Looks opposite. It's very sunny day. Maybe if it's colder, not maybe, sure, if it's colder day with the same irradiation, we will have higher output voltage. And important, it's mandatory to use solar panel with both poles, positive and negative, isolated from the ground. This is an example. We have a motor 460 VAC, and the panel is giving in output voltage in open circuit at the maximum temperature, the lowest, ambient temperature, 43.3 volts. This is a real example. So the calculation says 800 is the maximum. We divide by the voltage, and then we get 18 panels in series. This is the maximum number of panels in series that we can connect to the system, to this inverter. Here is an example of PV string configurations. Depending on the pump capacity, we need to put some strings in series, and sometimes we need to put in parallel to achieve the power of the system. And of course, it depends on the characteristics of the panel. If it's 20 or 30 or 35 volts, and as well the power, which is the panel watt peak that is giving. Normally, the engineering company or the company that is offering the panels can give all this information. And the recommendation to put the panels in series to get the maximum voltage, and then strings in parallel to achieve the maximum necessary power. Some desired features in a solar inverter, some functions related to the panel, like MPPT function, I have explained before, observer, big step, instability, to manage instability, I will explain a bit, as well recognize when there is low power coming from the panels. We have functions as well related to the pump, PID function, sleep, wake up function or dry pump, and functions related to the tank, to the storage, in order to manage, to control the level. This is, as you know, depending on the area, we have different irradiations. But we have, independently of the irradiation, we have different curves depending on the ambient temperature. So the drive is always searching for the point to get the maximum power. And again, we need to be careful and consider always that at the lowest temperature, we are going to get the highest voltage and the highest power. MPPT, this is the function, one of the functions, the important functions that this drive has implemented. So what it's doing starts, of course, what we want is to take the maximum power from the solar panel. So it starts at a voltage about 0.55 volts, and then gets some current. The next step that the drive is doing is decreasing the voltage and trying to see if it can get higher current. In this case, yes, and is getting as well higher power. So continues doing the same operation. Now moves to another point, reduces the voltage, again gets higher current, so gets higher power. We go in the good direction. Moves again, reduces the voltage. In this case, may get a bit higher current, but at the end, the power, the output power is lower. So the drive recognizes that's not the best point, the maximum power point, and then it's moving to the previous point and staying there. And the drive is continuously searching for this point. Sometimes the system starts at a lower voltage. So here we can see it's a bit less, 0.49, and then we get some current. Is same, reducing the voltage, but in this case we get a bit higher current, but the output power is less. So here this point, so recognizes that this is not the best point, goes back again, and then continues doing this operation in the opposite direction, and then recognizes that there is more power. They can get more power from the panels, but of course we need 3 points to see if this is the best point. So moves again, increases the voltage, and now gets less current, less power. So recognizes this and goes back and stays at the point of the maximum power. Okay, this function is an important function, and I would say, as far as I know, only Fuji Drive has this function, and this is when the cloud is passing through the panel. Of course, it's affecting very much the radiation, and then that is received by the panel, and then the output power of the panel as well is modified. What does happen? Many systems, when there is a step down, means we are getting a radiation, and suddenly this radiation drops down significantly. Then the normal operation is to stop the pump. There is no power enough, let's stop. But it's not good to start the stop, as we know. So in this case, the drive, what it's doing is searching for a lower point with a lower irradiation. Instead of stopping, is moving to another point. It's reducing the speed of the pump. Of course, we can put a minimum speed, but it's trying to, above this minimum speed, to search for a point where still can drive the pump. So that's what the drive is doing. The MPPT function is a lowest speed function. It's continuously checking, but it's a lowest speed. So it's a very good function and traces like the sun during the day. But of course, it's not moving at a fast speed. A cloud is. And this function is protecting, is helping that this cloud is not affecting the system. So this is the step down. Step up is opposite. A cloud is there, and then suddenly there is a much higher irradiation. So a system, what may happen is that the system becomes unstable. So the drive has some function to recognize there is a huge sudden change in the irradiation, in the power that we are getting, and then is searching a point, but in a stable way. And then, of course, with the MPPT, searches for the maximum power point and stays at this maximum power point. Now, these are some examples, and I would like to explain a bit what can we do with this system. If we have a drive that allows us to different connections, then we can have a system that is a multiple system. And we can have a system for pumping water, for pumping to the storage, to the field, etc. We can have as well, if we want in the system, some HMI giving us all the information, how much are we pumping, if it's already dry, how many hours, flow, etc. This is another example of flexibility. If we have already a PV system, a PV plant, then we can have an off-grid solar system with this PV plant and have multiple pumps. In this example, we have 3 pumps, and then depending, of course, on the power we can take of this plant, we can use this power for these different 3 pumps, and at different times. We can operate them independently. Another, of course, possibility is IoT, remote monitoring, remote control. We can do this as well. We can include these kind of functions in the system. I would like to give an example. This is a German company called Vispiron. They design a container solution, and this was a partnership among KSB, pump manufacturer, Fuji Electric. We were supplying the inverter technology plus some IoT solutions on HMI, and they were supplying all the solar system and building this kind of system. This is a chunky system, putting everything inside, all the parts were inside, and they were able to dispatch this container to any location, assemble, disassemble, wherever needed. So this is a real case using our solar drive. So some conclusions: merits: allows to obtain water economically, efficiently, and reliably by using this photovoltaic solar energy. Is autonomous system without human supervision. So some specific functions to ensure a continuous operation are embedded in the system, in the drive. Starts the pump when the condition, of course, is irradiation, are suitable automatically. Always obtains the maximum power from the solar panels thanks to this MPPT, maximum power point tracking function. Stops the pump depending on the operating conditions as well. There are some protective functions. Low pump rotation speed. There is not enough power coming from the PV panels, or the tank, the storage level is already full, or we are operating under, the well is dry, so there is no more water. There are functions as well to protect the pump in these cases. And protect the pipe in cases of overload, operation in dry well. Off-grid, one single interface for the end user. This is a possibility for small systems. We can have just the drive in a small box, and the keypad of the inverter would be enough to manage the entire system. We can even monitor through this keypad the current, the power, the voltage coming from the panel, the motor frequency, the current, the consumed power, etc. Very easy commissioning, depending on the system, between 6 and 10 steps, and we have the system running. Is able to control both asynchronous induction motors and synchronous, permanent magnet synchronous motors. We have experienced both systems, both kind of motors. And that has been, from my side, the presentation for this product.
Solar up, but I'm really excited as to the work that you guys have done. So thank you.
Thank you. Thank you very much.
Yeah, thank you, Matt. Well, Matt and John Williamson own Farm Data Systems, and they have designed some pretty amazing technologies over their company history for the last 20 years. They have a lot of the self-contained, pump control monitoring, irrigation automation, crop monitoring, and reliability of the networks is very strong. And they have a lot of the tools that can go right into the HMI. They also have a very huge SCADA system that allows to look at all the pressures, the flows, and necessary requirements to really keep those pumps operating at an optimal efficiency point. They also do a lot with voltage monitoring, because a lot of the systems that I have seen in the market, as far as the solar systems that had been currently used in the United States, is they were taking the DC power, using an inverter, converting it to AC, but tying it directly back to the power line. Well, from that, when you monitor in some of these rural areas, we're seeing tremendous voltage instability. So like Jose was talking about, over in India and different areas where they don't have stable power supply, as we've had in the past. And so what's happening in America, we're getting some of the similar issues of instability. I think I have someone on there that I may need to mute. Just 1 second. So the thing that has come about from that is that their automation system also measures, voltage A, B, and C, and checks that, because as I've seen some rural areas, when the solar systems come on and they tie that into a rural location, it'll drive that line voltage up on line A and line B, as much as, well over the capacity requirements of the electric motor manufacturers, and then you have motor failure. So there's been a lot of advantages that have came about. And again, the big part is actually, the remote control ability of, controlling those pumps. The other thing is that they're very heavily involved in is, well efficiency. Matt's been involved with Madeira Pump for several years also. And with what's happening, to the water levels, and the, lower water level that we're pumping from, it's drawn a lot of issues about, efficiency of that pump. And, Matt, you could probably jump in here better and explain this than I can. But the real issue is, the area where, they start, getting the water below where the screen levels are, cause, many things inside the well.
So thank you, Roger. Yeah. One of the, as we look at, the complexity of irrigation, over time has been very simplistic. We see the simplicity going away with, a higher demand for water, and with declining groundwater, we're going to have way more sophisticated strategies on how we irrigate, how we schedule, how we use our pumps, how we use our power. I look at, we're south of Merced, so if you put your finger in the center of California, we're south of what they call the rain curtain. So our average rainfall is about 12 inches, but we're right on the northern part of the San Joaquin Valley. The San Joaquin's about 5.8 million acres. It produces 7% of the value, ag value, of the U.S. So it's an extremely strong region, amazing soils, but water's our issue, and how we use water is going to be way more, as I said, more sophisticated and more complicated. I think what I see coming down the pike is that if I just broke up Madera County, we're going to see PG&E favor larger growers. But if you looked at the larger growers, you probably got 5 to 10% of those growers. And if I just broke up, and I'd say that if I just said there was 1,000 growers, about 700 are growers that are lower than 200 acres. And they're going to need this technology, because PG&E is probably not going to be enticed by small farmers, but it is a huge market, because at the end of the day, growers are going to need to access power. They're going to need to access solar because of the cost of power, and it's just really logical. So this solution for us is straight away. But again, it's part of the the solution. The ability to to control, sense, and monitor exactly what's going on in your crops is going to be more and more critical. And I think people are starting to recognize that. If you'd have said, pump control or anything like we're talking about right now, I think for the most part, people would have just kind of said, nah, that's never going to happen. But the water is driving it, and I think it's driving it globally. I mean, I don't think there's any place globally that's not concerned with groundwater. So we're trying to put controls in place. We're trying to put more monitoring in place, and for us, the ability to match pumps to the requirements of smaller blocks, and then using off and on grid control is going to be essential.
And so what they've done is they basically have taken a lot of the industrial platform technology that is out there, and I come from that industry for many years, and ag just really wasn't that detailed with using it, but the costs on the platforms, but also when you have people with the amount of experience in pumping and seeing the the right ways and the wrong ways things should be done, really make it a very sound solution. And so they do have it where they can put it to the phone, they put it directly to your computer, and then we can also put it directly to what they call an HMI on the pump panel systems that control the VFDs. And I just highly recommend moving to the VFD technologies that can take that multiple source, have that software designs and the designs of the way they've done their transistors or diodes and details inside. And we're coming from a very strong company it's been doing this for many years in many industries. So I think we have a lot of positives there.
I think you hit on something that's really important, Roger, is the fact that that we landed on an industrial SCADA platform. It's used globally, and obviously we've fit it to agriculture. Agriculture tends to be a little bit hard to deal with just because of the environment. For all intents and purposes, control has always been in a building, had the flexibility of no dust, no wind, no heat, and Jose mentioned that. I love the idea of hearing a controller. I mean, we set PID loops now for pressure, right? I'm fascinated to hear that that a controller, a drive, can actually look to see where it should source that power, whether it be the grid or off grid, and the blend actually optimizes our design on our pumps. I think that's going to be critical. But going back to it, irrigation is going to become way more sophisticated, and we know globally that food is going to be something that is a major driver. I mean, up to this point, we've been very fortunate to have a surplus, and I think that we're getting to a point where now people can afford to use this technology. It's critical to use, and I just see us. I think the future. Fuji has obviously put their best foot forward and come up with a solution. I think that's going to work really well with our control systems.
Yeah, so you might just speak briefly what this is about, uniformity there, Matt.
Yeah, thank you, Roger. I mean, one of the things that we see is, so I'll back up just a little. Not only do I have a pump company, but my background is in irrigation engineering. So as I look at an irrigation system, the critical link is if I had a block that was, let's just say it's 20 or 40 acres, what's critical to that block is that I have distribution uniformity from one corner to the other. That what's required there is pressure and flow. So as that system runs and irrigates, it's going to be critical to monitor the pressure at the farthest ends of the field to make sure and assure that you have high uniformity. So if I'm trying to break uniformity down, if you just looked at 15 trees on a hose, right? And in a high uniformity system, those 15 trees would all produce, right where the manifold started, it would produce 100 apples, and at the very end, it would produce 90 apples or 95. In an ununiform system where the pressures vary as the system, as the groundwater declines, you can see the uniformity in that system on those 15 trees. It can go from 100 down to 60, and at the end of that hose run, at the end of the the drip line, if you're only producing 60 apples at that end, that can equate up to 25 to 30% of your field. So the critical link is to have that uniformity across the entire block, so that you can you're assured that the water, the fertilizer, the inputs that you're putting are at a 90 plus distribution uniformity, and that's what we try to target. And what's critical about that is the power input and the design of the pump, and then our ability to watch flows and pressure.
Right. So if you can get those signals back from that, Fuji control of what capabilities are there, and they can give it an analog signal or a digital or whatever they want, back into your system, then you can go ahead and cycle, when you should irrigate. But when you've got the actual settings and monitoring of what, how many acre feet you're getting to certain areas, this will give you the consistency to still maintain that, 98 apple tree, in the far corner, but, make sure that it's gotten its uniform water. They've also went very heavily, into, tracking, all those various pieces of the system. So they can look at all the different sets, all the different areas, all the various pumps, in multiple locations. The other area that I want you to speak on just a little bit is Matt's been very heavily involved in also moisture, of the tree, of the water, where it's getting to, what depths. And so maybe you can jump in on this, and I'll let you talk about the, the sensor and where you came from on that.
Yeah, thanks, Roger. Again, when you start looking at sensor technology, our ability, all we see is above ground on a tree. But 50% of that tree is below ground. And what we have a hard time understanding is the dynamics in the soil. Soil has a lot of variability, so it's really critical to be able to put a set of sensors. So just picture down in the ground 5 feet, just a single probe, but there would be 5 sensors on that probe every foot. So when you turn that irrigation system on, you literally could see where that water and how long it took to get to each foot. What's critical for us, and what we're really looking to drive, is we're trying to reduce, all inputs, right? So fertilizer is a huge input for us. The active root zone of and I'll use an almond, is between 12 and 24 inches. In my soils, I have what they call an infiltration rate, which means that the water moves through the soil at about 1 inch per hour. So it is critical for me to irrigate that crop at about 12 to 18 hours, because I can target my nitrogen right into the active root zone where I'll get the highest efficiency of uptake. A lot of times what people will do is they'll run off peak, which means from Friday night to Monday. That's a 66-hour run. In my soils, that would put that water at 66 inches. So our ability to look under the soil, understand exactly what's going on both with water and fertilizer, is critical. And the one thing that nobody really pays attention to is that crops require 3 things. Light. Doesn't have to be sunlight. Obviously, hydroponics just needs light. Water, and then oxygen. And oxygen is the one thing that nobody understands or even thinks about when you're growing crops. But our ability to look in the soil and understand, that we're not saturating that soil is critical as well. So when we start running our system, our idea is to actually have those sensors, those 5 sensors at 1 foot, actually be able to call out the irrigation and say, in this block, I need to run approximately 12 hours. I'm going to start my fertilizer pump, 2 hours in. I'm going to shut the fertilizer pump 2 hours before I shut off the irrigation, and that'll target my active root zone. As we get better and we gather that data and understand it as it comes in, we've got machine learning, sitting right there in front of us, and that will be critical in resource conservation. We think that as important as just, being good growers, producing high quality, high nutrient crops, our ability to reduce greenhouse gases are going to be a huge component, and I think a revenue stream for us as well. So I think when you start talking about using solar, off-grid, understanding your soil, reducing fertilizers, all those controls are going to come into play down the road.
Well, I just know that the more and more that we collaborate together, through these groups, it seems quite amazing the various people that have came and brought different pieces together. But it's somewhat of a learning curve to start understanding and thinking about this a different way. And as soon as we become more acceptable to doing things different, this can't always just be the same. The more and more successful we're going to become. And I see a day where the sun comes up, the pumps actually pump when they want to pump, into the irrigation system. They're monitored, pumped how much they wanted to pump, and they're not, so reliant on that, only pumping on the weekends, because, I think some of that also definitely has to be offsetting, the quality of the crop. These are a few of the various growers and people, over 20 years that, Matt and his team have, operated and worked with, and, very happy to,
Roger, that you just hit on a really important point, is that as we get better and we understand, the actual biological functions of these plants, you're starting to talk about computational biology. And I think that's going to be critical both from a nutrition perspective, from a resource perspective, and just keeping those plants healthy and
again, monitoring those voltages. My father was a past president of ESA, which is a worldwide motor organization, and you can actually tell what has caused failures inside motors. And so a lot of those are coming back in, looked at what what they are and what they aren't, how they did work and how they didn't work and what caused them. And so we just want to keep that that motor that Tesla originally designed running with the proper power sources. We've been very heavily involved in turbine pump motors for years. One of our chief engineers started doing those back in the 50s, and built the high quality, high power motor. They also want to jump in here.
Yeah, Roger.
Yeah.
You got to thank you for putting that in, because I'm just as excited, from our monitoring perspective, is to look at the asset management side of it. Look at what a motor's what's going on as far as amps, heat, vibration. All those things are going to be critical to growers. I've got growers across the country right now that are, they had a really tough spring startup,
right.
and there's a lot of young guys looking at how do we understand these motors and what's going on. Just like we talked about crops, our ability to look at soil moisture, we should be able to see exactly what's going on with our motors.
Right, and when you have that monitoring capability and remote control and access, and look at vibrations, look at temperatures in the windings, you can preventative maintenance is huge. And you're talking a very expensive pump, very expensive turbine. If you have the automation tools which you have, you can set all those limits and take it offline, send the guy a message, an email, what, or, alarm him, directly to his phone that he, he'd go check that pump, because, otherwise maybe they didn't check it till the next day and they lost a day of irrigating, until they found out that something was, going bad. And then, it goes to a very critical failure instead of, just operating it correctly. VFD controls, do save a lot of money. I've been involved in, this happened to be a big chip burning power plant, up in New England. And, it does save a lot of money if you put the drives in correctly. And the benefit, that I found, working around Fuji is they build the steam turbines, so we're drawing, they probably don't know as much about irrigation, obviously, as, Matt and some of these people do, but the thing that they have is they have those resources, to help us get the right engineers, to look at this correctly. Let's see. I also wanted to bring up, and I saw that Rob was actually able to join in today, which I don't know if he would or not, but at the end of the day, the other big issue is back to the efficiency, of the pumps. And I've got involved with Rob Welke out of Australia, roughly about a year ago, and he also joined this Tesla group, and he has an amazing set of pumping curves, evaluation tools, to look at even what a lot of the pump manufacturers don't have, to get that efficiency of all the system correctly first before you even start to look deeper at putting how much solar and how much horsepower is on there. I know when Matt and I, when we first looked at one of your pumps, you had I think it was like a 50 horsepower submersible, in there getting a couple 100 gallons a minute out of that pump, and when they got the pump changed, ended up, I think, putting a 40 horsepower on the motor, and he's now up about 400 gallons. And so it's very important, through this process, that we also have the access to the engineers that can help,